Okay, welcome back. This is the second talk on the SPI bus, and this time I'm going to focus a little bit more on the SPI implementation on the Blackboard and Zinc processor. So here is a block diagram of the Zinc showing that the SPI block is one of several I/O processor / peripheral blocks available to the Zinc processor. All of those I/O peripherals, of course, compete for the limited number of pins available on the outside of the chip. And so the multiplexer-shaped block labeled MIO is showing that of all the I/O peripherals, I think I counted there's almost 200 pins between them. An user has to choose which of those blocks actually get to route to the limited 54 MIO pins on the outside of the package. If you want to use more of the I/O peripherals, then you can hook up to those pins. You can always run the peripherals into the FPGA through the EMIO bus, and then you can map those pins directly through to physical pins that are otherwise assigned to the FPGA fabric. And I think a little later in one of the projects, or maybe we've already done that, we've looked at configuring the MIO system. Anyway, in this case, I want to talk about just the SPI blocks. So the SPI controller, like most other peripheral circuits on the Zinc, is just a separate piece of IP that was purchased and assembled into what the Zinc device ended up being. And the IP block, that peripheral IP block, sits on the AXI bus like all other peripherals. And so the way you interact with the SPI controller is through a set of registers that the ARM can target over the bus. And this table shows you those registers. So by reading and writing the various status and control registers, you can completely control the flow of data in and out of the SPI port. So like the UART controller, the SPI controller contains FIFOs. In this case, though, there's two FIFOs, and they're 128 bytes each. They're one for reading and one for writing. Unlike the UART port, there are two different registers you can read for reading and writing. And now you know you kind of need that, because as data flows through the long shift register that is the SPI port, you need to have separate ways to both read and write data into that space. So I'll show you the addresses a bit later. They were in the previous table, and I'll show them to you again. But the read address for the receive FIFO is offset 20 from the base address, and you can see the write FIFO offset is 1C offset from the base address. 128 bytes, and you can configure the SPI controller to automatically start working as soon, if you're writing an SPI data point, as soon as you write a point into the FIFO, you can configure the SPI controller to automatically start shifting that and sending that out of the SPI port. And when data comes in, of course, it'll be automatically parallelized and placed in the receive FIFO, and then you have a couple of ways of being alerted that new data is ready. So if you look at the registers available to control FIFO operations, I guess I'll get there in a second. Here's a couple of the main registers. The top register definition, this is out of the user manual page on the website. The top register is a status register, and it provides, looks like, 7 bits that you can go read to tell you the status of the FIFO. Things like an underflow detected, meaning the FIFO's empty, you've tried to write more data than was there. Read FIFO full, read FIFO not full, and so on. So as the FIFO the read and write FIFOs are doing their things because you've written data or are receiving data, you can go read these bits to learn the status of the FIFO. The second register I showed is the configuration register, and you can kind of read through those bits to see what they do. They set up the clock source, They set up the phase of the clock and the polarity of the clock, the overall mode, whether you want to be a slave device or a master device, and so on. And in the project, in project 6, I write what you should do with each of these bits and kind of what the bits do. Now, I didn't detail the registers that you would configure to enable interrupts on the port, and that is part of what we want to do is set up the interrupt system. Essentially, what you're going to do is enable interrupts like you did with UART, set up the GIC to process an interrupt from the SPI port, and then these very same status bits that you can go pull can also generate interrupts. So it's not too big of a step, I think, to go from understanding what these bits do to setting up an interrupt system to respond to them. Gosh, why is this here? We just talked about this. Not sure why that's even there. I'm going to skip right over that slide. Okay, so the baud generator takes the system clock. On the blackboard, we set the clock driving the SPI port to 166 megahertz. You can change that if you want to. I don't know why you would. It's an adequate frequency. So you configure the SPI clock by putting a number in the divisor bits 5 down to 3 of the configuration register, and that divisor is used as an exponent to 2 plus 1. You can see the formula there to come up with the SPI clock. And in general, it really depends on what SPI device you're running, but in general, targeting somewhere in the 10 megahertz to 50 megahertz range is good for most SPI peripherals. If you really want to move data more quickly, you can increase the system clock from 166 megahertz a little bit, and you can use a smaller divider. But in general, somewhere in that range. So to configure the SPI controller, I took these steps right out of the Xilinx Technical Reference Manual just to show what their recommendation is. The first thing they want you to do is reset the SPI controller. Now there's a bit of a process involved to do that. The SPI controller is one of those shared resources that lots of different applications might want to be using to move data. So you don't want one application resetting or otherwise changing parameters without, I guess, the consent of the other applications, because if you reset it and some other process was using it to move data, you might mess up what that other process was doing. So to reset the SPI IP block, just like and to reset the I2C IP block and other system level blocks, you've got to do a bit of a procedure that involves unlocking access to that register. Now keep in mind the SPI block is a separate IP block. So the unlocking of the SPI access isn't really central to the ARM. It's more having to do with the IP block itself. It's outside of the ARM process. So all that happens is someone designed a kind of a register, a magic register, that you have to write a known random, semi-random key value to, and I'll show you what that is in a second. When you write that known key value to an unlock register, only then are you allowed to change how the port is configured or to reset it. And the thought is that would be extremely unlikely to happen randomly. To randomly write the single address that where the unlock key is stored, and then to write the exact right data, it's just very unlikely. So it's just a little more protection to make sure that applications don't accidentally overwrite or reset those sort of IP blocks. So I'll talk about that on the next slide. Once the controller has been reset, then you can program the clocks to get the proper clock frequency. Then you can configure the SPI controller, and you can do things like set a point in the FIFO at which you want to know the status. So it's a 128 byte read FIFO. You can set up a read value to say when it gets to be 2/3 full, or when it gets to be half full, then alert me. Then set one of those status bits that we talked about, and then you can additionally make that status bit create an interrupt. Or same on the transmit FIFO. Maybe you want to be alerted when the transmit FIFO has only got 10 locations left. You can set a value to compare to the overall FIFO depth and alert you when there's only so many data points left in the FIFO. So configure the SPI controller for the application you have in mind. Then you can configure interrupts, and that'll go follow very closely the procedure that we used last time to configure the UART interrupts. You'll set up the GIC to allow interrupts and to specifically allow interrupts from the SPI controller. You give it a priority, set the level or edge sensitivity, and then you'll configure the SPI controller to let it create interrupts. So there's a couple of register rights in there to set that up. And when that's all done, then you can start the transfers. So let's talk about those steps in a bit more detail. So again, the controller is a protected resource that has to be unlocked, and the SPI controller registers are just one example of several of what are called system level control registers, SLCRs. All of the SLCRs, and there's probably 100 or so of them, have to be unlocked before they can be read or written. And you can see here access is unlocked by writing DFOD, no idea why they chose that bit pattern, to address F800-0002. The chip designers chose that address and that code for whatever reason, just to make sure you're purposefully going in to do something with the system level control registers. Okay, and to do the unlock sequence, here's a bit of C code, and this is taken directly from the project. Defined the constants that are appropriate here, the addresses for lock and unlock and reset, and then the lock key and unlock key. And then the code itself is real straightforward, except for that for loop in the middle there. And the reason we put the for loop in there is that the Xilinx technical reference manual is a little bit cryptic when it says how to do the reset process. It literally says, and you can go read this, it's in the TRM, it says write ones to reset the various subsystems, then, and I should have put quotes around it, let some time pass, and then write zeros. It just doesn't say how much time. So I'm sure that for loop that we put in there with an index of 1000, I'm sure that could be pretty much any number. It could probably be 10 or 1, or maybe it would work just fine without that for loop. But because it wasn't specified and because we've got no real time constraints on this program, we just threw 1000 in there to be extra safe and extra conservative. So that code works, and you can use that to unlock the SPI controller and then to relock it when you're done. Okay, to configure the SPI controller, these 11 points pretty much talk about the 11 bit fields in the control register. If you go back and look at all the fields in the control register, you'll see that these are the 11 fields. And I'm just telling you here, showing you how you can set them to set up the SPI controller appropriately for this project and for just about any project. So the first thing is we're gonna be the bus master. So the mode fail bit is set to a 1 to say that we're a bus master. You could set it to 0, in which case you want to be a slave to some other SPI master. In that case, it's not going to try to generate mode fails, which we're not even going to talk about here. So set manual command start to 0. That means that when you put data in the FIFO, the SPI controller will automatically start sending data. If you set that to a 1, then you would manually go write another register to start the SPI bus working. And same thing with bit 3, set manual start enable to auto. Enable manual chip select. Now, well, CS is, first of all, so somebody in the documentation called the Xilinx signals CS instead of SS. So for this discussion, CS, chip select, and SS, slave select, we're going to use interchangeably. So the reason we want to have a manual chip select in this project is because, we'll see a bit later, the device we're talking to, which is the nav chip that's got an accelerometer and gyro and magnetic compass, magnometer, has two separate SPI ports. So the reason we're using a manual chip select is so we can manually choose which of those SPI ports into the device we want to drive. If there was only one slave select, one chip select for the device, we would not needed to have done that. We could do an auto chip select, but in this case, we need to switch between two different SPI ports. It's the same chip, same device, but the designers of it chose to have two independent SPI ports. So that's why we're doing enable manual chip select. And then we're going to set CS to 0F to start with to deassert all of them. Now later, 0.6 there's a 4-bit field in the control register, and the 4-bit field, you're going to write to it one of those three patterns. So, 3 don't cares with the lowest significance bit 0 selects chip select 0 to drive. The next pattern with the lower 2 bits 0, 1 selects chip select 1, and the next pattern 0, 1, 1 selects chip select 2. So in that 4-bit field in the control register, that's how you're going to choose which chip select that the SPI controller is going to drive out into the outside world by writing one of those patterns. And more on that when we get to that point here a little bit later. So 0.7 is you can, if you wanted to have even more chip selects, if you wanted to have up to 8 or 16, if you set the external decode bit, then you could route the slave select bits from 0.6 into a decoder. And you could use them to create a larger number of slave selects. Well, we're not going to do that, so we'll just set that bit to 0. Master clock reference, we want to choose the SPI reference clock, the 166 megahertz clock we routed to the SPI controller, so that's 0.8. 0.9, if you choose 32, I guess we're going to, now that I read this point, the nav chip needs an SPI clock below 10 megahertz. So if you choose 32 or even a larger number, you'll set the frequency to below 10 megahertz as required by the module. So you might as well just use 32. And then that device, the nav chip, is defined to use SPI mode 3. So we're going to set the clock polarity to 1 and the clock phase to 1 to select mode 3. And finally, we'll put the SPI, make sure it's in the master mode. So those are just the bits in the control register, and I talk more about that in Project 6 as well. After having done that, now the SPI port's ready to use. And if you write any data into the transmit FIFO, the SPI controller will automatically send it out the SPI port. As mentioned, we're going to use the SPI port to talk to the LSM9 inertial module that contains the accelerometer, gyro, and magnetic compass. That's the point of this project. Okay, so this next slide, the next slide shows you where the datasheet is, if you want to go read that. I guess the last point on this slide is important. It's connected to SPI port 0, and there's SPI controller 0, and there's 2 SPI controllers on the chip. We're using SPI controller 0 for this project. Okay, here's the picture I thought was on the last slide. So this is showing all of the SPI ports on the blackboard. Now we're interested in the SPI ports connecting the zinc to the LSM9, and that's shown in the kind of upper half of the block diagram. And you can see the very top 2 pins there. SSO hooked to K17. K17 is the physical pin on the outside of the chip package on zinc. And the logical node slave select 1 is hooked to physical pin K16. And those 2 pins you can see on the LSM9 are connected to the 2 chip select inputs. So if you are using the SPI 0 controller, if you look over in the darker blue rectangle inside the zinc there, you can see the top controller is labeled SPI 0 controller. So if you're using the SPI controller 0, and you manually enable slave select 0, you're going to be talking to the accelerometer and gyro. The CS_AG signal, that means chip select for the accelerometer and gyro. If you manually select slave select 1, you're going to be talking to the magnetometer. That's CS_M connected to K16, means the chip select for the magnetometer. Now from the picture you can see that S clock is the same, MOSI is the same, but MISO is different. There's a different data pin connecting the MISO from the accelerometer and gyro to the chip, and also a different one for the MOSI, for the magnetometer, I mean. So we took care of that for you in the FPGA. We detect if slave select 0 is being driven. We switch the mux so that the channel connected to the accelerometer and gyro passes back to the arm. If you select slave select 1 to talk to the magnetometer, then we automatically switch the mux to bring the MOSI from the magnetometer back to the EMIO interface. So it's pretty simple. All you have to do to talk to one of the instruments is choose which slave select you're going to drive in the control register of the SPI controller. I hope I didn't make that too confusing. It's about as simple as we could make the board. So on the last part of the slide here, to configure the SPI port to talk to the LSM9, those are the things you want to do. Make sure the SPI port is in master mode. Make sure you're using mode 3. Set the divide clock to 5.2 megahertz. And no external decoder, manual chip select, and automatic start. Okay, and again, I talk more about this in the project write-up as well. Just kind of a high-level picture of the LSM9, showing what the ports look like. Again, showing that clock and MOSI are common, but the selects and the MISO signals are separate for the two instruments. And that's pretty much all handled for you by when you manually select which port you want to write to. The interrupt signals in the bottom, we're not going to use those at all, so you don't need to worry about those. Here's a quick look of the registers available inside the LSM9. In the early part of the project, you're just going to read the Who Am I register to see who you're talking to. These are the two different ports. One port is for the LSM9's accelerometer and gyro. That's the top table. And you can see over on the right of that table, it says SPI controller 0, slave select 0 is how you talk to that. And then the magnetometer is SPI controller 0, but slave select port 1. And so you can use these addresses to read the data from those devices. To read data from the LSM9, you can go, again, read project 6. If you want to read data from a particular register, you can actually configure the device to write the address and then read the data, or they all default to just spitting out data in the most likely way you're going to want it. What's this slide for? I guess showing that, yeah, all transfers are 16 bits long. So when you're reading data, yeah, that's what I wanted to show here. This is how the data is going to be formatted. So if you're going to read, notice the very first bit on the far left is called read, not write, RW with a bar over the W, meaning if that bit is a 1, you want to read data. If that bit is a 0, you want to write data, followed by the address of the register you want to access. And those addresses are available in the table above. And then comes the actual data. So let's see here. So to do a read, you would set the read bit to a 1, send the register address in the next 7 bits, and then send 8 zeros. and those 8 zeros would force the data through the shift register back into the MISO signal. To write data, you'd set the write bit to a 1, then send the register address, and then send the actual data you want to write. Okay. So last slide, quick summary for SPI communications. Enable the controller by writing to the Zinc SPI ER register. Assert the gyro SS signal by writing 1110 to the CS bit field in the configuration register. And actually, I think the leading bits don't care, but if you write 1110, that will select the chip select associated with the accelerometer gyro. If you write 1101, that'll select the magnetometer chip select. Then you move data through the SPI registers by writing the RW bit for a read or for a write, then writing the register address, and then writing 8 zeros to send data out or read the data if it's coming in. You can pull the transmitter FIFO underflow from the status register, or you can set up an interrupt to alert you when there's 1 or 2 or however many points left to read. Read the data bytes from the received FIFO, and there'll be 2 of them. And then you can, when you're done, disable the SPI controller. That's pretty much it. So I think you'll find some good explanation and maybe some sample code. I believe one of the TAs was going to put a video out there giving you some more insight into writing code to control these things. But I'm hopeful with that information you can go and attack the project and find success. Well, that's about all I have to say for SPI operations. The next couple of lectures will cover I²C, and then we're rapidly kind of heading towards the end. I want to do another couple lectures, one on memory systems and one on motor control, and then some wrap-up information, and that'll be it. So we're more than halfway through, I'd say, this learning at a distance portion of the class. All right, see you next time.